everyone, my name is Abhishek Pandey. I am a Prime Minister Research Fellow in the discipline of Mathematics at IIT Bhubaneswar. Today we are going to talk about week 11 assignment. My audio is I'm audible, na? Rajesh? So let's start. So this is the first question. Basically it is based on the logarithm, branch of the logarithm. So the first question is, if omega is subset of C is simply connected, then there exists a holomorphic branch of the logarithm. Okay. So let's start this question. First let me denote something. So basically, as we know, like this argument, okay, so you define the argument from C star. So basically C star is nothing but C minus 0. R. So you know that argument of Z basically theta, okay, where theta satisfies isn't it? Yeah. So now you can see that this for a particular value of Z, basically this theta, this argument will give different thetas. Okay. And all the thetas will differ from 2k pi. Okay. So to make it as a function, okay, we need to choose unique values of theta. Okay. So what we will do, we will restrict in some interval of length 2 pi. Okay. So you can choose any interval of length 2 pi and fix that argument of Z belongs to that one. Okay. So if we choose the interval minus pi to pi, okay, sorry. If I choose argument of Z belongs to this one, so we call it as a principal branch of the argument, okay, and we denote it by argument of Z. Okay. Now argument of Z is basically, now it is a function. Okay. And basically the range is minus pi to pi. Okay. Is it clear? Yeah. Anything? Yes, sir. Is any doubt? Yeah, so that, see, at minus pi and pi it will have same values. Yeah, isn't it? Like cos minus pi and cos pi is same. Okay. So one thing we have to exclude. Okay. Like also you can consider it as 0 to 2. Sorry, 0 to 2 pi also. This interval. Okay. So there also you can define this argument of Z, small arg. Okay. So there that will be a function like single valued function. Here it is a multi-valued function. Okay. Now since this is defined, we can talk about this continuity and discontinuity. So basically discontinuity, can you guess, or I mean, can you intuit what kind of discontinuity it has? I mean, at what points? This capital ARG. Okay, so now you take the this negative real axis. Okay, so now once you you take any point on this one, you converge from upward side and downward side, okay, like from upper half plane, lower half plane, okay, through this line. So once you take this sequence, okay, once you take this sequence, you will converge, this argument will converge to pi, okay, and once you go to from this side, argument converges to minus pi, okay. So you have a same two different sequence converging to same point, but argument converging to different points, okay, capital ARG. So this is basically discontinuity of argument is basically z such that x is less than equals to 0, comma y equals to 0. Is it clear? Yeah. So we call basically argument to the, like we call argument as a principal branch. Principal branch of argument. Okay. So now you can see that once you and suppose if you take this one, okay, here I have restricted in minus pi to pi, okay. Now suppose if you restrict in this one, okay, so basically you will get the discontinuity this line, okay. So it will be, so once you define this capital ARG, it will be discontinuous on this positive real axis, okay. So anyhow, the way you are choosing this interval, you are getting this discontinuity line. So basically this, in general, this discontinuity line will be a ray from origin and making the angle theta, where theta is, so this making angle theta, where theta is like this. So like theta to theta plus 2 pi you can do, okay. So I hope it is clear now. So now if you understand the branch of the argument, you can like define the branches of logarithm and other things, okay. So like logarithm of z is defined as ln of mod z plus I into argument of z, okay. Now to define the, like this is also defined on c minus 0, okay. Okay, so this is defined on c minus 0 and this is multivalued since here it is small arg, okay. So you have to define some principal branch. So once you define the principal branch, we call it as log z ln of mod z plus I into principal, okay. So this is called the principal branch of logarithm. Okay, and you can see that like any branch of logarithm will have a discontinuity line passing through origin making some angle theta with the positive real axis, okay. So like this one, this log z has discontinuity on negative real axis, okay. Is it clear to you? So this is the way we define the branch of the logarithm, okay. So these things are very important in constructing Riemann surfaces, okay. Those things you will encounter later. So is it clear now, branches and all things? Yeah. So if I ask you whether uh, so does there exist a branch of logarithm in punched unit disk, Okay, so what will be your answer? Hello? So basically you can prove that there does not exist any branch of logarithm in punctured unities. Okay, basically here we have shown that, so basically any argument of any branch of logarithm will have a discontinuity on the line passing through origin and making some angle theta with the positive real axis. Okay, so all those lines will intersect with the punctured unities. Okay, so any branch of the logarithm will have a discontinuity in this punctured unities. Okay, so this is called the principal branch of logarithm and is continuous or moreover analytic, moreover holomorphic, morphic on C minus x such that x is less than equals to 0. Okay, so you just remove the negative real axis. Okay, then there it is, a holomorphic. So basically this you can prove also using Cauchy-Riemann equation. Now with these basic facts, let us move towards the problem. So let omega subset of C is simply connected, then there exists a holomorphic branch of the logarithm. Okay, so you simply take unit is. Okay, so unit is basically there is no holomorphic branch of the logarithm. Also at 0 it is not defined itself. Okay, so you cannot define a branch of the logarithm. Now the next question is, so if f and g are continuous branches of the logarithm, then there exists an integer k naught such that fz and gz differs 2 pi I k naught. Okay, so let f and g are continuous branches of logarithm. What does it mean? E to the power fz is equals to e to the power gz. Okay, now this will be e to the power fz minus gz equals to 1, basically 2 pi I k naught. So 1 is basically 2 pi I k naught for some k naught belongs to z. And this will imply fz minus gz is equals to 2 pi I k naught. So basically fz equals to gz plus 2 pi I k naught. Okay, is it clear? Yes. So basically the first one is false, the second one is true. Now let us look at the third one. So let omega subset of C star basically C minus 0. Here we have means. And f be a continuous branch of the logarithm on omega. Okay, then f is necessarily holomorphic even we don't assume that omega is simply connected. So basically this is true. You can prove it by Cauchy-Riemann equation, and also the way I have mentioned here, so any branch of the logarithmic is holomorphic only. Okay? So any branch of the logarithmic will be holomorphic. If it is like if there exists a branch of logarithmic on a domain, it will be holomorphic. Okay? So this is also true. Yeah. So now the next question is, this is a quite important question. Let omega be a simply connected subset of C and let f such that omega to C be holomorphic function. with no zeros, okay, on omega, then there exists a holomorphic branch G of complex logarithm of f. Okay, so this we will prove. So now let omega be a simply connected domain, and f such that omega to C be holomorphic such that fz is non-zero for all z belongs to omega. So then you can define this one, okay, and and clearly G is holomorphic in omega. Okay, is it clear? Up to this everything is clear. Yeah, and as omega is simply connected by Cauchy's theorem, you have this one, isn't it? For every closed rectifier curve in omega. Since G is analytic in omega, so and omega is simply connected, so by Cauchy's theorem you have this one. Okay. So now in earlier assignment you have seen that if over every integral over every curve of a holomorphic function is 0, basically that holomorphic function has a primitive. Okay. So and thus G has a primitive in omega. So say that primitive is f. Okay. Now fix a point z naught in omega and define h by this. Okay. So now here you observe that this log I am only defined at a point. Okay. So this is a constant. Okay. Yeah. I am not saying that it is a branch because we have to prove that it is a branch. So this is basically a constant only. Okay. So now you take the derivative, so it will be nothing but f dash. So basically h is also a primitive of G. Okay. Now the function capital GZ, this one. So this one is holomorphic in omega. Okay. Why? F is holomorphic, H is holomorphic, and this is basically a composition. Okay. And this is a multiplication. So is holomorphic also. Now once you calculate the derivative, what you get that derivative of this G, capital G, is 0. Okay. So G is constant in omega. Also G of Z naught is 1. Okay. So and G is constant, so G is basically identically equals to 1. Okay. So Gz equals to 1 for all Z belongs to omega, and hence Fz equals to e to the power Hz, and thus H is a holomorphic branch of log f. Is it clear?
Yes, sir, clear.
Yeah. So if you have a simply connected domain and non-zero holomorphic function on it, then you can always define a branch of log of f. Okay. This is the theorem. This is just an observation. Next one. This is true. And let omega be simply connected subset of C, and let f such that omega to C be a holomorphic function with no zeros. Then for any natural number n greater than 1, there exists a branch, holomorphic branch of the root function. Okay. So this is just so. Okay. So since omega is simply connected and this one f is holomorphic function, so means you can define the branch of uh, f, sorry, log of f, means there exists a function e to the h such that e to the power sz is basically log of fz. Okay. Oh, sorry, e to the power sz is f of z. Okay. So basically h is the branch of h is the holomorphic branch of f, log f. Okay. Now let gz is equals to e to the power hz by n. So basically once you do gz to the power n, you will get f of z. Okay. So here gz is analytic, holomorphic, and you get gz to the power n equals to f of z. Means g means you have proved that g is a holomorphic branch of fz to the power 1 by n. Okay. Means nth root of fz. Is it clear? Now so this is the domain that we have defined. So basically C minus negative real axis. Okay. So which of the following is true? So star shaped around 1. So do you know what do you mean by star shape?
No, sir.
So basically any domain is said to be star shaped if there exists a point P such that every other point of that domain can be joined by a straight line. Okay, to P. Is it clear?
Yes, sir.
Yeah. So as you can see, this one, here if you see, so here is your one, okay, and this is removed. This basically we have removed, okay, negative real axis. So you can see any point, if you take any point z0 wherever possible, this is straight line, okay, to 1 will completely lie on this one, this whole domain, okay. So omega is star shape. Is it clear to you? Basically you can check that, yeah, basically what you need to check is that uh, so suppose you have z naught, okay, so 1 minus t into z naught plus t into 1 is basically 1. This belongs to omega for every t belongs to 0. Okay, so this is basically a star shape. Is it clear? Star shape around 1. And also this is simply connected also. Now the next thing is the function log is a continuous branch of the logarithm, okay, on this one, like we have seen earlier, okay. So this is also true. Is it clear to you that this is a
Sir,
log
clear.
is a, and log is also holomorphic branch of the logarithm? Yeah. Now the function, this principal branch of logarithm can be extended to a continuous function on C star, okay. So this is not possible, okay, because any branch, any continuous branch of the logarithm will have a discontinuity on a ray passing through origin and making some angle theta with a positive real axis, okay. So this is not possible, it cannot be extended. This thing is clear,
Yes,
Rajesh?
sir, clear.
Yeah.
Yes, sir.
The function log is an antiderivative of the function 1 by z on omega. So basically this you can prove, this you can so easily. Basically e to the power log z is basically z. Once you do the differences by chain rule, you will get e to the power log z upon d by dz of log z, basically 1. Okay, so you will get that dy dz of log z is basically, and e to the power log z is basically z only, so 1 by z. Okay, so derivative is 1 by z. So this is true. Okay, is it clear?
Yes, sir, clear, sir.
Okay, now let us move to the third question. So let D denote the open unit disk and F says that D to D be a holomorphic function. Okay, which of the following statements are true? Okay, so now let us see the solutions of this one. Just wait. So it is saying that if f is an automorphism which has exactly one fixed point in D, then f necessarily the identity function. So you can construct the example. This is not the case. Okay, this is not true. Basically, I will give the idea. So basically, one thing you observe, this you have seen. Basically, all the automorphisms will have this form. Isn't it? So all the automorphisms of the unit disk have this form. Okay. So what you need to do now, you can, if you see this one, only this one, okay. So once you see this one, so it is a z minus a, z minus a bar z square, okay, and this is basically equals to z square is a upon a bar. So basically modulus of z square is basically 1, okay. So this thing, this does not have any fixed point in unit disk, okay. Just keep this in mind. So means for theta equals to so for theta equals to 1, okay, sorry, theta equals to 0, whatever the theta, so that e to the power I theta equals to 1. Okay. So basically you have to, like, the idea is you have to take the suitable theta so that this will be this will have fixed point. Okay. So basically in general you can see that a is equals to 1 minus a bar z into z. You can see this equation. Okay, so e to the power iota theta z minus a e to the power iota theta is basically z minus a bar z square. So this will be a bar z square plus e to the power iota theta minus 1 into z, okay, minus a e to the power iota theta. Okay, this thing is clear. So now,
Yes, sir.
yeah, so now once you equate it to 0, so now once you equate it to 0, you can see that this is a polynomial of degree 2 in Z. Okay, okay, this is a polynomial of degree 2 in Z if like this a bar, this if a is non-zero and e to the power iota theta is not equals to 1, so this is a polynomial of degree 2. Okay, so yeah, so in this case, there exists a fixed point of f. Okay, in this case, so you have to choose suitably that e to the power iota theta should not be equals to 1. Okay, because if it is 1, this equation doesn't have any solution in unit disk. Okay, yeah. So you have to choose e to the power I theta so that this is not equals to 1 to construct an example. Okay. Fine. Let us move towards the next example. If f is an automorphism which has two fixed points in D, then f is necessarily the identity function. Okay, so this we will see. Okay, so B. So let f belongs to automorphism of D. Okay, and z1 comma z2 be its two fixed point. Okay, is it clear? Yeah. So now what we will do is Now what you do is just wait. Yeah. So now you define gz is equals to z minus z1 upon 1 minus z1 bar z. Okay. Okay. So basically this sends z1 to 0. Okay, and g of z2 will obviously be non-zero. Okay, now you define h of z is equals to g composition f composition g inverse of z. Okay, now you can see h of 0 is basically 0. So once you put 0 here, it will goes to z1 and f has a fixed point as z1 and g of z1 is again 0. Okay, and h of g of z2, this is basically g of z2. Clear?
Yes, sir.
Yeah. So by Schwarz lemma, by Schwarz lemma, by Schwarz lemma, we have h of z is equals to z. Is it clear? This thing is clear or not?
Yes, sir.
Okay. So fz will be basically g inverse composition h of g of z. So this will be basically z. Okay. So f is identity. Okay. So this is true. And this is false. First one is false. So if f is an automorphism of D, then f necessarily extends to a continuous on D closure. So basically you have seen that it is nothing but z minus a upon 1 minus a bar z. So the only problem is when z is equals to 1 upon a bar. Okay, and this will be greater than 1 since a is less than 1. Okay, so on unit circle it is also continuous. Is it clear?
Yes, sir. Yes, sir.
Yeah. So this is true. There exists an automorphism G of D such that G does not extend to a continuous on D closure. So by the previous option, this is false in view of the previous option. So now given 2 points A and B in D, there exists an automorphism G of the unit disk such that G of A equals to B. This is true. Let us prove it. So this is basically so let A comma B belongs to D, okay, such that f belongs to automorphism of D. Okay. Now you have to prove that no, this is not the case. Wait. So you have to prove that there exists f belongs to automorphism of D such that f of A is basically equals to B. Okay. Is it clear?
Yes, sir.
Yeah. So what you do is you define two functions. f1 of z is basically z plus b upon 1 plus b bar z, and f2 of z is basically z minus a upon 1 minus a bar z. Okay. Now g of and you define gz is basically phi 1 composition phi 2 of z. Okay, so once you do, what you will get g of a. So g of a is nothing but phi 2 of a. Okay, and phi 2 of a is nothing but 0. Okay, and phi 1 of 0 is nothing but b. So you get this G basically belongs to automorphism, because these are automorphism, so composition is also automorphism. Is it clear?
Yes, sir.
Yeah. Now next theorem is quite important, which is known as the peak lemma. Let us see the last option. Okay. So this is basically, let a comma b be 2 points in the unit disk such that f of a equals to b, then this derivative at a is less than equals to 1 minus mod b square upon 1 minus a square. Okay, so this is quite important. This is known as Peck's lemma. This is true. Let us try to prove it. So a comma b belongs to D such that f of a equals to b. Okay, where f is nothing but D such that f such that D to C is holomorphic. Okay, now now what to, again you take phi 1 z equals to z plus a upon 1 minus z a bar z, and phi 2 z is equals to z minus b upon 1 minus b bar z. Okay, now what you do is you define gz is equals to phi 2 composition f composition phi 1. Okay, now what you will get, so g of 0 is nothing but 0. So basically phi 1 of yeah, so phi 1 of 0 is a, f of a equals to b, and phi 2 of b equals to 0. Okay, is it clear?
Sir.
Yeah, so by Schwarz lemma, modulus of g of 0 will be less than equals to 1. Okay, and basically what is this? This will be nothing but by chain rule phi 2 dash b into f1 dash, f dash a and phi 1 dash 0. Okay, so basically you will get that f dash a is less than equals to 1 by phi 2 dash b into modulus of phi 1 dash 0. Okay, and if you calculate, basically phi 1 dash z is nothing but 1 minus mod a square minus 2a bar z upon 1 minus a bar z whole square. So this implies phi 1 dash 0 is nothing but 1 minus mod a square. Okay, also once you calculate phi 2 dash z, so phi 2 dash z will be 1 minus mod b square upon 1 minus dz whole square b. So to calculate phi 2 dash b, so once you calculate this one, you will get 1 upon 1 minus mod b square. Now it is easy to see that modulus of f dash a is less than equals to 1 minus mod b square upon 1 minus mod a square. Okay, is it clear?
Yes, sir. Clear, sir.
Okay. Now let us look at the fourth question. So here D star is the punctured unit disk. Okay, so this one is this one you can see it easily. The point 0 is a removal singularity, because any deleted neighborhood of 0, f is bounded. Basically f is only D star to D star. Okay, so f is bounded. So 0 will be a removal singularity, isn't it?
Yes, sir.
Yeah. Now Now let us look at the second question. Okay. So option B. So option B, let us see. So if suppose that limit z tends to 0, mod of fz is greater than equals to 1. So if it is greater than 1, f will be discontinuous, isn't it? So basically once you define hz is equals to fz such that z is non-zero and limit z tends to 0, f of z, sorry, z tends to 0, f of z tends to 0, f of z if z is equals to 0. So if limit z tends to 0 modulus of fz is greater than 1, okay, then h is discontinuous. This one is clear? Basically you have a point in the unit disk which is converted to 0, and this mod of fz also belongs to the unit disk only. So the converging point modulus cannot be greater than 1. It will be discontinuous. Okay?
Yes, sir. Got it.
And now if limit z tends to 0, mod of fz is basically 1. Okay? So now you consider in okay. So if this modulus is sorry. Yeah. So if z tends to 0, modulus of fz limit is 1. So basically you have the punctured unit disk, okay, and you have a puncture at origin, okay. Uh, so you and f maps unit disk to basically the punctured unit disk to punctured unit disk, okay. Now you take any sequence converging to 0, okay. So now and observe that your f is basically, what is your f? F such that d star to d star is a holomorphic function. Okay. So as we know that, so any holomorphic function maps open set to open set. Okay. Any holomorphic function is an open web. Is it clear?
Yes, sir. Clear, sir.
Yeah. So once you take the any open deleted neighborhood of 0, okay, this should go to the open set, okay, but as you can see that limit z tends to 0, f of z is tending to the boundary, so you have to include this boundary point 1 also. So the image of this, okay, will not be open, isn't it?
Sir.
So this case is not possible. Okay, so limit z tends to 0, mod of fz has to be less than 1. Okay. Okay. Now, now your H is basically D to D is analytic. Okay. Now this H, now this is also this basically less than 1. So basically your H is analytic from some unit disk to unit disk. Okay. Is it clear?
Yes, sir. Clear, sir.
Yeah. Now basically what is the third one? So this is true. This one is also true. So we have to prove that basically that limit z tends to 0 f of z is 0 only, nothing else. Okay. So basically since so H maps open set onto open set and F is a bijection on T star. So basically this gives that H of 0 is nothing but it has to be 0. Okay. Okay. So basically H of 0 is 0. Now, so this gives the proof of this one, third one. Oh, wait.
Sir, here we take
Wait, wait,
zero.
wait, wait. Yeah, sorry, sorry, wait, wait. I think, yeah, here it is, fz is any holomorphic function, okay? Fz is any holomorphic function. So this is not true basically. If f is an automorphism, basically here I've written, if f is bijection, okay, on D star. If f is an automorphism, then this holds, okay? For this you can construct some examples, okay, for only holomorphic function. Yeah, any doubt? You are telling something?
Here our domain is D star and pointed itself origin. So can we take zero?
No, no, 0 we cannot take. But we are defining, since 0 is a remote singularity of f, so we can define analytic function on the unit disk. Basically just taking this limit. So this will be analytic, isn't it?
Yes, sir.
This H will be analytic on D. But we don't know whether this range of H is lies in unit disk or not. Okay.
Okay, sir.
Yeah. So that we have proved here. If this limit is less than 1, so basically H says that D to D is analytic and D to D is analytic. Okay.
Okay.
Yeah. And since S is holomorphic, H maps open set or to open set. And F is a bijection on D star, so you can see this one.
Okay.
Yeah. Now H of 0 is 0, so you can apply Schwarz lemma. Schwarz lemma will give you mod of Hz is less than equals to Z mod Z. Okay. Now you take in Z naught belongs to D star. Okay. And modulus of Z naught will be nothing but F inverse F of Z naught. Isn't it?
Yes, sir.
Yeah. So this will be less than equals to mod of F of Z naught. Okay. Which means modulus of H of Z naught. So by 1 and 2, we have modulus of Hz is basically equals to mod Z for all Z belongs to T. Okay. So basically Hz is what? A rotation. Okay. Clear? So
Sir, clear,
basically,
sir.
what we have proved that any automorphism, let me write it again. Any automorphism of punctured unit disk disk is a rotation. Okay, so this we have proved. Okay, so this is also true. Now let us move towards the last option, last question. So basically there is some problem in this question. Some misprinting is there. So I will rewrite in a new way. So this fourth condition, you consider it as f of 1 by 2 equals to 1. Okay, and this one you just consider, then evaluate 25 modulus of f of 1 by 5 plus 9 modulus of f of 1 by 3 plus 1. Okay, this you evaluate. Okay, so now let us solve this question. So f says that d to c is holomorphic. Now you define gz is equals to fz by 2. Okay, so modulus of gz is basically less than equals to 1, and by open mapping theorem basically g maps d to d. Okay, and g of 0 is basically 0 by this one. Okay, this one. So using this we have proved that g is less than 1 modulus of g, and using this we have proved that g of 0, 0. So now by Schwarz lemma, modulus of gz is basically less than equals to 0. Okay, now you see that g of 1 by 2. Okay, so what will be g of 1 by 2? It will be modulus of g of 1 by 2, it will be 1 by 2, isn't it?
Yes, sir.
Yeah, so gz is nothing but e to the power iota theta z for some theta. Okay, this is clear. Now now what is derivative? G dash z is nothing but f dash z by 2, which is equals to e to the power iota theta. Okay, okay, and also what will be g of g dash 0? G dash 0 is nothing but 2i by 2. Okay, so g dash 0 is nothing but I. Okay, so what you will get, e to the power iota theta is nothing but I. Okay, so gz is nothing but iota z. Okay, so this implies fz is nothing but 2 iota z. Okay, now you can calculate. So 25 into modulus of f of 1 by 5 plus 9 into modulus of f of 1 by 3, 9 into modulus of f of 1 by 3 plus 1. Okay, so this you will calculate it as, so 2i upon 5 plus 9 into 2i upon 3 plus 1. This is modulus. Okay, so this will be nothing but 10 plus this will be nothing but 6 plus 1. This will be 7. Okay, so we are done with the assignment. Any question, Rajesh? Any doubt? If you are having, please let me know.
Not from assignments, sir.
Yeah.
I have another doubt.
Yeah, please tell me.
Sir, about removable singularity.
Yeah.
Sir, like if we have analytic function,
Mm-hmm.
so it is differentiable on whole complex plane.
Mm-hmm.
So, sir, does it have the removable singularity?
You have an analytic function. It is holomorphic on whole complex plane.
Yes, sir.
So it is entire. It doesn't have
Yes,
any
the entire
singularity.
function. The removable
No, no, so it doesn't have any singularity. Entire function, it does not have any singularity. No? Basically, removal singularity means any function if it has a removal singularity, basically it means you can,
The Lorentz series
yeah,
expression
yeah. So
does not contain negative power.
yeah, negative so it will be
coefficient
only
in
the
it.
power series terms. Okay.
Yes, sir.
So any analytic function having a removal similarity at some point, basically it means that you can see that analytic function as an analytic function in the whole, okay, the whole domain. Where it has a removal similarity, there also you can consider it as a holomorphic function. Although there it is not defined, but removal means you can define in a way so that it will be holomorphic. Okay, so this is what removal similarity means. You can consider it as a holomorphic function. Is it? Does it clear it out?
Yes, sir. Yeah.
Okay.
Thank you, sir.
Okay. So we will meet in the next session. Okay. Thank you.
And same time, sir.
Yeah, like Friday. Friday
Yeah,
timing.
Friday.
Yeah, Friday timing.
Okay.
Okay.
Okay. Thank you, sir.
Okay.